Great. Thank you for the invitation and the introduction. I'm Kenji from the Applied Engineering Physics. I joined about a year ago, and so far I've been, having a lot of fun here, both in academics as well as going to the waterfalls and things like that. So today I'm going to be talking about the most of the works that I've been doing during my postdoc. So I have presented maybe like 3 times or something in Cornell already. So, some of you might have had almost the same talk. I'm sorry about that. We are studying a lab yet, and we have a couple of new results, but they're still too early to put it for the presentation. So it's mostly about what I've been doing during my postdoc. And today I'm going to be talking about how to create ferroelectrics by using the van der Waals materials and van der Waals heterostructures. Specifically, I'm going to be talking about how we can create, the ferroelectric materials starting from non-ferroelectric materials, but by stacking them by the interlayer interaction between the layers, we will be able to engineer the ferroelectrics. So that's the idea that we have been pursuing. And it turns out that it's also both interesting from the physics as well as application perspective, which both of them I'm going to be talking about today. And feel free to ask me any questions. It's kind of like internal, colloquium. So feel free to ask me any questions in the meantime. Okay, so let's start by the basics of the ferroelectrics. I'm sure that many of you know about it. One of the most typical ferroelectric materials is one of the most well-known ferroelectric material is the barium titanate. Here you can think that this titanium ion is not comfortable at the center of the cube of the perovskite, but instead it's shifted either upward or downward. And because this titanium ion is positively charged, it creates a finite electrical polarization or the dipole moment. And the nice thing about this ferroelectrics is that it's not only have a polarization, but also we can switch them by applying the external electric field. So we will be able to, if we can switch this polarization nicely, we will be able to use it for the non-volatile memories by thinking this down polarization and up polarization as being 0 and 1s. We will be able to store the information in a non-volatile manner. So this is nice, but if you look at your computer, you're not using these ferroelectrics for the memory application at least. And one of the biggest problems here is that, it's really difficult to make this ferroelectrics material thin while preserving these nice ferroelectric characteristics. And that's a big issue because these ultra thin ferroelectrics is essential for creating a dense storage. For making the size of the devices to be smaller. First of all, we need to have the thin film, and also it's important for the energy efficient switching considerations because as you make the materials to be thicker and thicker, the required voltage for the switching gets larger, which means that you require a larger voltage, larger energy for the switching. So we really need to solve these problems from the material science perspective. And there has been a lot of development in this field. For example, using the hafnium oxide or using the gallium nitride and the aluminum gallium nitride. Scandium gallium nitride. Sorry, scandium aluminum. Wait, scandium aluminum.
Askin. You want us to ask?
Yeah, aluminum. I felt like something was weird. Sorry. Anyways, there has been a lot of development in these fields. But especially if you stick to the perovskite oxide, it has been really difficult to make this, preserve these ferroelectric characteristics while, making the thin film to be thinner. One of the biggest problem is that, you have the surface dangling bond, and this surface dangling bond basically screens the ferroelectric polarization. That's called the depolarization effect, and that destabilizes the polarization of these materials. So one of the solutions is to use the materials that doesn't have a dangling bond, and that's the 2D materials. So that's the field that we are working on. The nice thing about these 2D materials is that we will be able to exfoliate these, for example, bring the bulk crystal of graphite, exfoliate it, and get the ultra thin graphene or the monolayer scale of graphene. And this is an image of the graphene. You can see this in the pink color. You'll be able to distinguish between the substrate and the graphene. And the nice thing about this is that we will be able to apply this technique to the other materials as well. So we can, for example, do the same thing for the boron nitride. as well as the semiconducting transition metal dichalcogenides, or the superconductor, ferromagnet, or the ferroelectric materials. Even more nice thing about these materials is that after obtaining these monolayers, we will be able to reassemble them together to create the new structures. So one thing we can do is, for example, we put the boron nitride on the graphene as well as a transition metal dichalcogenides on it, which of course doesn't exist in nature. So we will be able to create artificial structures that doesn't exist in nature by reassembling these monolayer thickness materials. The other thing we can do is that we can put the two layers on top of each other, but now with a finite angle between them. And we will start to see the long range patterns that has a much longer periodicity as compared to the original lattice constant. That's called the moiré super lattice. And in some sense, this is kind of like changing the lattice constant between the each of these bright spots. So by using these techniques, we will be able to control the crystal symmetries, crystal structure, as well as the lattice constant. So we can already see that we will be able to play with these materials and engineer the new properties that each of these layers doesn't have. So one of the most famous example is probably the magic angle twisted barrier graphene. We put the two layers of graphene with a finite angle of around 1 degree. And then because this moiré super lattice is kind of dilute, we will be able to gate it and control the numbers of carriers or the number of electrons for each side, each of these moiré side. So one thing we can do is, for example, if we put the three electrons here, we will be able to see the magnetism as well as a quantum anomalous Hall effect, where the whole resistance is quantized at the zero magnetic field. And also we will be able to, instead of putting the integer number of electrons, we will be able to put, let's say, 1.5 electrons here, and then we will be able to see the superconductivity. And the nice thing about this is that we will be able to tune between them simply by the electric field. So this is something that we couldn't do in the conventional materials. We will be able to dramatically, because of the formation of the moiré bands due to the band folding, we will be able to study by changing the carrier density, we will be able to position the chemical potential to the different places of the Fermi levels that leads to the various different types of the emergent phenomena. So the the important message is that if you focus on these interfaces, these interfaces is the source of the emergent physical properties. So based on these previous works, what we considered is that if we can engineer the ferroelectric materials by stacking the non-ferroelectric materials. So that's the questions that we are going to be answering. The conventional ways of obtaining, if you focus on the two-dimensional ferroelectric materials, the conventional ways of obtaining the ferroelectric material is to start from a bulk ferroelectric materials. And for example, we are showing the crystals of the indium selenide. And because of the weak interaction between the layers, similar to graphene or graphite, we will be able to exfoliate it and obtain the ultra-thin indium selenide down to the monolayer while preserving the ferroelectric property. So this is nice. We will be able to obtain atomically thin ferroelectric materials by the exfoliation. But of course, this method is kind of limited because we, first of all, need to start from the bulk of layered ferroelectric materials, which, as you can imagine, is quite rare. So our approach is instead of starting from ferroelectric materials at the beginning, we start from non-ferroelectric materials. But by stacking them, we asked ourselves if we can create the ferroelectrics by the interlayer charge transfer. So that's the question that we are going to be answering today. Okay, so the materials that we focused on is the boron nitride. So here is the crystal structure of the boron nitride. This is a bulk boron nitride crystal structure, and we can see that this a boron nitride forms this kind of a honeycomb lattice, and neighboring side consists of a boron and nitrogen. So instead of carbon to carbon, we have a boron and nitrogen. And what we can see also here is that if you look at the neighboring layers, the first layer and second layer, the two layers are rotated by 180 degrees, which means that in the first layer, the top of the hexagon is a nitrogen, but in the second layer, it's boron. So it means that because of this anti-parallel stacking of this boron nitride, this material itself has a center symmetry. If you do the inversion operation against here, boron goes there, nitrogen goes there, boron goes there. So it as a whole crystal, this boron nitride has an inversion symmetry, which of course means that you don't have any polarization. Okay, so that's the natural crystal structure of the boron nitride. But we can also engineer the crystal structure of this by using the van der Waals heterostructure techniques. One thing we can do is, for example, we can prepare the monolayer boron nitride and cut it into half and then stack them on top of each other. So then we will be able to obtain a different crystal structure from the original one because the two layers of boron nitride is now stacked in the parallel directions. This turns out that this structure is energetically unfavorable because now you have a nitrogen on top of nitrogen. So because of the electrostatic repulsion, this structure is energetically unfavorable. So naturally, this structure becomes either the AB or BA stacking structure, which are energetically degenerate. And in the case of the AB stacking, for example, we will have the vertical alignment of the boron and nitrogen. And what happens is that there will be a hybridization between the two PZ orbitals of the boron and nitrogen. And that results in the charge transfer from the nitrogen side to the boron side, which means that we will have the finite electrical polarization in this AB stacking structure. So this is the case of the AB stacking. And we can also look at what's the BA stacking look like. And it turns out that in the case of the BA stacking, you now have a nitrogen on boron, which means that you will have an opposite direction of the polarization. In this case, the charge transfer happens from the bottom layer to the top layer. But for the case of BA stacking, you have the charge transfer from the top layer to the bottom layer. And what's interesting, yes?
I'm just not familiar with this field. You talk very casually about taking monolayers of atoms and cutting them and stacking them and shifting them. So is this this is easy to do?
Yeah, so we literally physically do this manipulation. Yeah. We will be able to find the monolayer first by the microscope, and then we can literally cut it. For example, by using the AFM tip, we will be able to cut it, okay, and then use the polymer to pick up one of them. That's half of this flake, okay, and then do the same thing for the other flake. So because the original crystal is a single crystal, if you do the pickup of the two layers, these two layers is pointing in the same directions, which means that they are stacked in parallel. Does that answer?
This is done routinely.
Yeah, so we
simulations in a particular orientation is favorable.
Right. So we will be able to, if you start from the single crystal, what the other thing we can do is that we pick up one layer and then rotate the substrate and then pick up the other layer, so that we will be able to control the, as you have seen the picture of the moiré superlattice, we will be able to control the angles between the two layers. So
is the apparatus to do this very sophisticated?
You just need a microscope and the manipulator. Really? So it's like something you can, I don't know, you can even do at your home.
I mean, Kenji makes it sound easy. It was that easy. There are so many 2D materials that will be doing this, right? So you can count who's actually producing results, right? So what's the yield? Yeah, let me put it the other way. What's the yield?
Yield is not that bad. For example, for the devices that we have tried to make ferroelectricity and seen the ferroelectricity is, I think, more than half when we aimed at it. Sometimes we don't see it it's not difficult to characterize why don't we see hysteresis if you don't see it. But the yield is at least more than the 50%.
Is it set up in your lab now?
Yeah.
To do this?
Okay, thank you.
Thank you. Okay, let me go on. So the nice thing about this two stacking structure is that we will be able to actually switch between them by the interlayer sliding motion.
Can I say something?
Yes.
Actually? Sorry. Kenji said yield is 50%, but it's for you, yield is 50%.
Yes. That's true.
So if it's a second year grad student doing it, what do you think the yield will be at the beginning?
2%.
No, it's not that bad. No, it's maybe like 40%. Anyway, so thank you for the comment. Anyway, so yeah, let me explain about what happens if you do the interlayer sliding. So you start from the AB stacking and you slide the you take a top layer and then like slide it by the one side of the unit cell, and then you can change to the from AB stacking to the BA stacking. It might be more clear if you see it from the side. Initially, you have the AB stacking, you have boron to nitrogen alignment, and then as you slide the top layer, it becomes a nitrogen to boron alignment, and that results in the switching of the direction of the polarization. And you can see that this is actually quite different from the conventional mechanism of ferroelectrics. For example, if you think of the barium titanate, if you apply the electric field, the atoms or the ions moves in the same direction as the electric field. But in this case, what happens is that as you apply the out-of-plane electric field, these atoms moves in the in-plane direction, and that results in the switching of the out-of-plane polarization. So that's something unique to these materials. And this really comes from the anisotropy in the strength of the bonding between the interlayer bonding as well as intralayer bonding. So that's why we call these materials as a sliding ferroelectricity or the interfacial ferroelectricity. Okay, so that's the background. And the question is how we measure this ferroelectric polarization. The method we took is the create a ferroelectric field effect transistor, where so this is the device structures that we made. We have the graphene, and beneath this we have the parallel stacked bilayer boron nitride. We have the two monolayers of boron nitride stacked in parallel, and in addition to that, we just have the conventional non-ferroelectric boron nitride on top and bottom, and this just serves as a gate dielectric. So this is you can maybe think of it as just aluminum or something, aluminum or something. And so we will be able to, for example, apply the gate and tune the carrier density of the graphene, or we will be able to, if you apply the backgate between the graphene and the backgate, this is the metal. If you apply the voltage between the graphene and backgate, we will be able to also apply the electric field to these ferroelectric materials. So this device structure is called a ferroelectric field effect transistor. What happens is that depending on the direction of the polarizations of these ferroelectrics, we will be injecting either the negative charge or the positive charge to the channel layer. So by simply measuring the resistance of this channel layer, we will be able to tell the direction as well as the magnitude of the polarization. So in some sense, this graphene works as an electrical sensor for detecting this ferroelectricity. So let me go into the experimental result. So we first start by applying the top gate to the between the metal and the graphene, and we don't see anything special. We just see the resistance peaks coming from the charge neutrality point of the graphene. So this is completely irrelevant to the ferroelectrics characteristics. This is just a simple transfer curve of the graphene. We have the resistance peak at the charge neutrality point, and we don't see any hysteresis by scanning of the top gate in the forward or backward directions. What's interesting is the backgate. If you sweep the backgate in the forward and backward directions, we see the clear hysteresis depending on the scanning directions. Okay, and we also see, if you focus on these tiny regions, we will be able to also see the jump in the resistance. Jump in the resistance at a certain electric field. So this jump in the resistance comes from the ferroelectric polarization switching. As you apply the electric field between this graphene and the backgate, we are applying the, have an electric field applied to these ferroelectrics, and that leads to the switching of the polarization. So that leads to the jump in the resistance as well as the hysteritic behaviors.
Yeah. So you're saying that when you're doing a top gate, your ferroelectric stack doesn't feel, there's no electric field now kind of like seeping.
To be precise, there's a slightly very small electric field. I would say maybe 20 times smaller electric field because the graphene is not the metal. You have the finite, density of state. It does not completely screen the electric field, and it has a finite electric field going out. But that's much smaller than what we can apply with a backgate.
I see. And then, so the CNP changing. So I was thinking about this as in like, if your carrier density is a little higher, what is the modulation in your channel carrier due to the polarization switching at a much higher density level?
Are you asking, for example, about here?
Yeah, or like if I'm sitting at 3 volts, would I
Right,
see?
so
would
in
you be
3 volts, we
sensitive?
cannot see we cannot realize, we can only realize up polarization because this is the field that
yeah,
polarization
got it.
switching happens.
And then, the layer sliding is a lot of energy to slide.
It is.
So if you think about, okay, I want to switch my polarization versus layer sliding energy, yeah, what's the energy scales?
So energy scales, if you calculate the energy of the polarization P times E and compare the energy scale of delta, it's actually the electric field here is about 10 times smaller than the energy scale of delta. So that's kind of what usually happens for the ferroelectrics. What happens is that you don't really need to go over the delta completely in order to switch it. You still have a imbalance between the different polarization state. And then what happens is that there's some like nucleation side of the domain wall or the domain. And then because once you nucleate the domains, this expansion energy, it's a kind of like competition between the domain wall expansion energy as well as domain flipping energies, right? And then we will be able to, even if it doesn't go over delta, we will be able to switch it still.
I see. So then do you think it's homogeneously everywhere single domain, or it's domains of both polarizations, but just whichever wins?
So yes, we think that the switching happens by the domain wall motion. So there is a domain. And it is actually quite important for the switching. Thanks. Is there any other question? Good. So yeah, we have the top gate and back gate. So now we can sweep them independently.
And I'm sorry. So what happens at room temperature? What's the behavior at room temperature?
I will talk about it.
Oh.
So we now have the top gate and back gate simultaneously. And then we can, in the left side, what we are doing is that we are sweeping the back gate in the decreasing direction. In the right side, we are sweeping the back gate in the increasing direction. So what happens is that how you can see it is that this is a charge neutrality point of the graphene. And then this charge neutrality point of the graphene suddenly shifts from the right side to the left side to the right side, or the right side to the left side. And that corresponds to the switching of the polarization. As the polarization direction switches, this ferroelectric material introduces an extra charge carrier to the graphene. So based on this, we will be able to actually calculate the magnitude of the polarization, by looking at how much it shifts. And that's about 2.25 picocoulomb per meter, which actually agrees pretty well with previous theoretical values before our experiment. So this gives me the evidence that this ferroelectric hysteresis really happens from the sliding of the two-dimensional ferroelectric materials. The other thing we can do is that we will be able to measure this. We have the Hall-bar of this graphene, and we can now measure this resistance from the top side as well as the bottom side of the Hall-bar. And these two looks almost identical, except this region, the intermediate regions, which happens during the switching of the polarization from downward to the upward direction. And if you take a line cut, we can see that we have two peaks. And these two peaks comes from the polarization up as well as the polarization down. So we can see, it tells you that there is a coexistence of the up and down polarization here. So what we think is happening is that we start from the down polarization, AB stacking, and then you nucleate this up polarization, BA domains. In between, you have this kind of a domain wall that spans around 10 nanometer. This domain walls moves is somewhere in that orbit, and then finally expanded to the whole region of the device. So does that answer your question? So we think that we will be able to also actually visualize it in using a PFM that I'm going to be showing you later. So yeah, of course, this is at the low temperature, and you'll be, of course, interested in what happens at high temperature. And it turns out that this ferroelectrics is highly stable against temperature. So you only changes the polarization magnitude about, like, let's say 3% as you go from the lowest temperature to the 300 Kelvin. So this tells you that this ferroelectrics is highly robust. And we will be able to also see it, the hysteresis at the room temperature. So this is the hysteresis behavior at room temperature. And we will be able to also see the jump in the resistance coming from the polarization switching from downward to upward and upward to the downward directions. So this is nice. This is the original goals that we wanted to realize. You will be able to now obtain the atomically thin ferroelectric material. Each of these thickness is 0.33 nanometer. So the total thickness is less than 0.7 nanometer. But now we will be able to realize this ferroelectrics, which is stable at the room temperature. So that's nice. And we started to also investigate the possible application of these materials, especially as a non-volatile memory. One thing we have checked is that how robust this ferroelectric polarization switching, polarization direction is against the time. And what we have done is that we set the direction of the polarization to be up or down, and then measure the rebit in the room temperature, and then checks the direction of the polarization after 1 month. And we have shown that the direction of the polarization remains the same directions after 1 hour at least. After one month at least. The other things that would be interesting to explore is that how fast we can switch the direction of the polarization. Of course, if it takes about a second for switching the polarization, it's not really useful as a memory. We would like it to be, at the switch this polarization at the speed of the, clock hertz. So what we have checked is that how fast we will be able to switch the polarization. And the way we did is that we first set the direction of the polarization to be up, and then apply the downward electric field with a different pulse width, and then checked if the polarization direction is switched or not. So this is a result. We changed the pulse width from the spanning about 10 decades, starting from 1 nanosecond to 10 seconds. And then we applied the various height of the pulse, and measured if the polarization is switched or not. So this red region corresponds to the polarization up, a blue region corresponds to polarization down. So the regions that the color changes corresponds to the electric field we require for the given pulse width. So we can see that as you make the pulse width to be shorter and shorter, we require a larger and larger electric field for the polarization switching. But the most important point is that if you zoom into this small time scale region, we'll be able to still see the polarization switching even at the 1 nanosecond time scale, which means that as you apply the gigahertz pulse, we will be able to switch the direction of the polarizations. So that's nice, and we can kind of see that if you extrapolate, it's not like the end. We might be able to even apply the smaller pulse. Currently, it's of course limited by the electronics, but if you, for example, use the optical method, apply the terahertz, we might be able to switch it even at the picosecond time scale. So that's one of the things that we are interested in. And the other things that we have checked is that how robust this ferroelectric polarization switching is against the repeated switching cycles. And it turns out that this ferroelectric switching is highly robust. As you switch it many times, the material really doesn't seem to degrade. So we can have shown that we will be able to switch these devices about 10 to the 11 cycles. And this is actually quite nice because most of the ferroelectric materials, as you do the repeated switching cycles, the material itself degrades and it no longer functions as a ferroelectric non-volatile memory. And the main issue comes from the fact that as you switch the polarization direction repeatedly, the interface starts to degrade, or an interface starts to accumulate the charge, and that results in the degradation of the performance of the ferroelectrics. In our case, because we are relying on this interlayer sliding motion, it doesn't really damage the interface, and that's what we think is the reason reason why we have the high endurance cycles. Okay, so so far so good. So that's about the application, and of course we have just shown that it's we can do this kind of thing for just one device, or the few devices, I'd say. But it's of course if you talk about the application, it's of course important to grow these materials in the wafer scale. And there has been a couple of reports that people have grown it by the CBD or the MBE to grow this parallel stacked boron nitride. It's not the most energetically favorable structure, but using using the terrace of the substrate by using the miscut substrate, people have shown that we will be able to grow the boron nitride always in the same direction, and that way, people have shown that they will be able to also see the PFM hysteresis. So I think this is a pretty promising directions. We are hoping that we will be able to grow the similar kind of things in the paradigm here. Is there any questions so far?
Do you have a PFM map? Do you have a map of the domain boundary for your device?
For our device, yes, I will be showing it later. All right, so that's for the case of the parallel stacking. What we have shown is that as you make the stacking order from like anti-parallel stacking, 180-degree twisted stacking to the parallel stacking, we have changed the characteristics of these materials from non-ferroelectric to be ferroelectric. And as I mentioned in the beginning of the talk, we have the extra degrees of freedom in the 2D material, which is the twist angle. So the natural question is, what happens if you do the twisting between the two boron nitride? Will it be ferroelectric or the non-ferroelectric? So we can answer this question by looking at the crystal structure of this boron nitride. If you twist them parallel stacked boron nitride slightly, we will be able to obtain this kind of a moiré pattern similar to the graphene. But it's actually not identical to graphene because the A sublattice and B sublattice is not identical in this case. So what happens is that we now have this AB and BA stacking locally, and that has the opposite out-of-plane polarization. We also have this AA stacking regions, but this AA stacking region is energetically unfavorable. So there is a competition between the interlayer bonding as well as interlayer and the interlayer bonding. And then what happens is that these atoms moves to shrink the size of this AA stacking. And as a result, we get this kind of a triangular patterns consisting of up and down polarization directions. So that's what we visualized by using the vertical PFM. So PFM is a method that is, we will be able to detect the direction of the polarizations. What we do is that we apply the out-of-plane voltage and see how the tip is deflected as you apply the voltage. So we are measuring the piezoelectric effect. And what we can see is that we have this kind of AB and BA stacking structure. And these upward and downward triangle have a different contrast, which means that these different stacking order indeed have an opposite out-of-plane or the different polarization magnitude. So that's what we call moiré ferroelectrics. It's nice that by simply twisting the two layers, we'll be able to get this kind of alternating out-of-plane polarizations, which I believe is almost impossible in the conventional ferroelectric materials. So we would be interested in how the ferroelectric behaves in this twisted boron nitride. So okay, sorry.
Will you talk about those lines? It's not just triangles, but you have this like extra.
Right. So we have the slide for that. So the way we should think about it is that we actually have a two contribution of the piezoelectric effect, which is one of the piezo response from the ferroelectrics. The other is what's called the flexoelectric effect. We have the gradient of the strain at the domain wall because of the relaxation of these atoms at the domain walls. We change from AB to BA, which necessarily leads to the gradient of the strain, and that also causes a piezo response. And so you can think that at the domain wall, we will have the extra contribution of the piezo response in addition to the ferroelectric contribution. Does that make sense? It's like we have so what we are interested in is this, but it's inevitable that because we have the gradient of the strain at the domain wall, we cannot really pick up only this contribution, and we always have the extra contribution of the flexoelectric effect at the domain wall.
So where the strain is maximum and where the switching happens are different locations. Where the gradient of the strain is maximum, I guess.
The maximum strain happens at the middle of the domain wall, like here.
Where is the middle of the domain wall?
Like let's say here.
Uh-huh.
Or maybe here actually, because it's kind of like a topological defects.
Okay.
I'm not sure if I answered your question.
Actually, I don't know what I'm trying to ask either, actually.
Okay.
But I mean, so I noticed, because I'm thinking, shouldn't you have the lines in all three parts?
Yeah, we don't have a full understanding of this the image.
Mhm.
It's a bit, it's not easy because there's also background signals that, so we cannot like see the full sine reversal of like 180-degree phase difference in the up and down domains because of the small piezo response. We just have 2 layers, and also the piezoelectric coefficient is not quite large. So we cannot see the full reversal of the phase by 180-degree. That makes the interpretation a little bit difficult. The bottom line is that we don't really fully understand what how we should think about the image at the domain wall. Yes.
Would EFM be expected to give a clearer picture?
Right. Yeah, exactly. So I don't think I have the data, but we will be able to do the KPFM, the Kelvin probe force microscopy, which is you are measuring the surface potential directly, and that gives you the more clear signal. Yes. We are doing it, but I don't have that data. Yeah, so in that case, we don't see anything like from the ferroelectric effect. We just see the contribution from the ferroelectrics. All right, so sorry, this is not. Yeah, this is how the device looks like in a large scale. So you have the 2 layers of the boron nitride, top and bottom, and we don't see any features at the monolayer regions, like either in top and bottom. But at the intersection between them, we will be able to see the nice these triangular patterns that comes from the ferroelectric polarization. Another thing you can notice is that as you go to the edge of the samples, the angle between the 2 layers kind of relaxes because that's the energetically most favorable state. So you start to see the larger triangular patterns as you go to the edge of the sample. All right, so that's what we are measuring, and we will be interested in what happens if you change the twist angle of the 2 layers. So the original structures that we have measured is a non-twisted device. We have the 2 layers of boron nitride in parallel, and we see the sharp switching of the polarization as a function of the electric field. So that's what we have observed. But if you twist them, the behavior changes dramatically. The polarization changes much more gradually as a function of the electric field. And we can interpret this by the formation of this moiré ferroelectrics. In the moiré ferroelectrics, we have the lots of domain walls, and each of these domain walls basically moves independently. So it has their own quasi field. So that's the reason why the polarization switches much more gradually. And also we can see that the quasi fields that we require for the switching is smaller because you have the pre-existing domain walls here. So they are basically free to move. So maybe this kind of like gradual change of the polarization could be useful for, let's say, the neuromorphic computing or the analog computation. Right. Yes.
For the twisted case, it looks like the switching is starting before the electric field direction changes.
That's true. Yes. What happens actually is that at the zero electric field, if you don't have any pinning, this is the most energetically favorable structure. So if you make the twist angle to be gradually change the twist angle from 0 to like let's say 1 degree, at the large angle, which I mean by like let's say 0.5 degree or something, you don't see any hysteresis. That's because you have this kind of structure. And it, of course, the structure changes by the electric field. But then if you don't have any pinning of the domain walls, you should not see any hysteresis, right? Does that make sense? Because that it's for these devices, it's the most energetically favorable to, at the zero electric field, it's the most energetically favorable to have the smallest length of the domain wall. So yeah, the reason why we don't see that we have the finite change already at zero field is that these structures are energetically favorable. Of course, in the real device, we do have a pinning size, and that changes the scenario, but that's how you interpret this.
Isn't there a torque on the twisted layer?
Could you repeat again?
Isn't there a torque on the twisted layer that will want to move it back?
It always happens. That's the reason why we see the, in these devices, we have, as you go to the, edge of the samples, we see the, the larger domains. It's difficult to relax at the center, actual center of the device, because that requires like you really changing the angles between the two layers of the entire sample, which is, quite hard. Right. So that's what we can do by the small angle twisting. If you go to a little bit larger twisting, we can also create a different game where we will be able to use this twisted bilayer boron nitride as a substrate for tuning the potential of the 2D materials. For example, let's imagine we put the graphene or the bilayer graphene on top of this. And then because of these finite polarizations from up and down directions, we will be able to introduce a periodic potential modulation to the target layer or any 2D materials. What happens here is that the original band structure of the graphene is kind of folded because of the existence of the periodic electrostatic potential modulation. And as a result, we will be able to get this kind of a folded band structure. So we can now use this twisted bilayer boron nitride to engineer the band structure in the momentum space as well. The result we get is something like this. We first see the resistance peak at the charge neutrality, but this is the typical for the graphene. But in addition to that, we also see the resistance peak at the electron side as well as the hole side. And also we see the sign reversal of the hole resistance at this resistance peak region. And this could be interpreted as an emergence of the extra charge neutrality point or the Dirac point at the electron side as well as the hole side because of the band folding of this graphene. We will be able to also change the angle between the two layers, and we can study how the resistance behavior changes as a function of twist angle. And what we can see is that as you make the twist angle to be smaller and smaller, we get the larger and larger moiré periodicity, and that results in a smaller Brillouin zone, moiré Brillouin zone. So we start to see the higher resistance peak at the smaller charge carrier density as you make the angle between the two layers to be smaller. So we think that this could be useful for the kind of like a universal ways of tuning the band structure of the 2D materials. And we can also see the post-data butterfly behaviors where we, in addition to as you apply the magnetic field, in addition to the lambda levels from the charge neutrality, we also start to see the emergence of the lambda levels from the extra charge neutrality point at the electron as well as hole side. So this is a case for the graphene, and the things that we would be that many people in the community is interested is that can we see for example, the correlated electron behaviors by creating the flat band in these by using this moiré structure. We don't see any hints of the correlation in this bilayer graphene, but it could happen if you go to the many more layers of graphene. People have shown that in the what's called the rhombohedral graphene, we have the mass, higher mass because of the flatness of the bandage. And people have, for example, seen the fractional quantum anomalous Hall effect by introducing the extra moiré potentials to this multi-layer rhombohedral graphene. So we think that we might be able to also use this twisted bilayer boron nitride platform for introducing the periodic potential and potentially realizing the strongly correlated phenomena. Great, I'm taking a lot of time, but let me also talk about one last stuff, which is that I've been mostly focusing on the boron nitride, and the question is that is this idea limited to the boron nitride, or can we apply the same kind of idea to the other materials? So it turns out that this method is we just need a simple component for doing this artificial ferroelectrics. We first need a honeycomb lattice, just like graphene. But unlike graphene, this A sublattice and B sublattice needs to be a different atom. In this case, boron and nitrogen. And as long as you satisfy these two conditions, we will be able to convert any 2D material to be ferroelectric. So one of the most famous example here is the transition method dichalcogenides. If you see the structure from the top, we will be able to see that we have the honeycomb lattice, and the A sublattice and B sublattice in this case is a metal and chalcogen. So we will be able to, by changing the stacking order, again, this is a natural stacking structure, which is non-ferroelectric, center symmetric. But by putting the two layers of TMDs or transition method dichalcogenides on parallel, we'll be able to also convert it to be ferroelectric. So that's what we experimentally observed by basically using a similar method. We place the parallel stack by a tungsten diselenide, apply the top gate, we don't see any hysteresis. But if you apply the back gate, we also see the hysteresis coming from the switching of the polarization of this bilayer tungsten diselenide. Which we can also do for the other materials, and we have shown that we can convert 4 semiconducting transition method dichalcogenides to be ferroelectric as well. If you look at the magnitude of the polarization is about the half of this the case of the boron nitride. We don't have a good explanation, but that seems to be consistent with the theoretical calculation. And the other thing we can play with this structure is that we will be able to directly visualize how the ferroelectric polarization switches in the real space by scanning over the sample in the device. So what we can do is that we can now create this kind of structure. We apply the electric field to this parallel stacked molybdenum diselenide, and then scan over the sample and see how the domain evolves as a function of the electric field. In this case, we are using what's called the lateral PFM, which is only sensitive to the presence of a domain wall. So we can see that at the boundary between the up and down domains, we will be able to see the contrast of at the domain wall. But anyway, if you follow this position of the domain walls, we will be able to see how the domain evolves as a function of the electric field. What we can see is that as you apply the upward, starting from a downward electric field, if you start to apply the upward electric field, this downward polarization domains gradually shrinks as a function of the electric field. So we think that a similar thing happens in the case of boron nitride, which means that by the domain wall motion, it's not the entire layer that is shifting simultaneously, but more like we start to create the small domains, and as the domain wall moves, we will be able to switch from the AB to BA stack. And of course, there are lots of things that we can play with. TMD is especially well known for its nice, light matter coupling. So we will be able to, for example, people have observed, it's not from us, but people have observed, for example, the photovoltaic effect because of the existence of the finite polarization. And then people have also shown that we will be able to detect the direction of the polarization by measuring the interlayer extons. So this shows that we are not doing the same thing as a boron nitride, but by applying this kind of same techniques to the other materials, we will be able to convert the interesting 2D materials to be ferroelectric. And that is nice because you'll be able to also think of varieties of different things. For example, converting the magnetic materials to be ferroelectric to realize a multiferric, or apply it to superconductors. And we may be able to switch the superconductivity by the polarization, or apply it to the topological materials, and we might be able to also change the topological numbers by the direction of the polarization. And some of them are already proposed in the theoretical calculation. All right, so that's the end of the talk. And especially, as I mentioned, this work was mostly done at MIT under Pablo Haro and with the grad student Shirei. And I also had a lot of feedback from the theoretical collaborators, as well as generous materials provider in NIMS, as well as from Columbia. with that, I would like to finish it. So the bottom line is that we started this journey from the, making these ferroelectrics, and we have, it turns out that by, using these materials, we can really play both in terms of the fundamental physics as well as application. And what we have shown is that we will be able to also use this sliding ferroelectrics for the non-volatile memory and apply it to the other materials, or use this twisted boron ferroelectric, moiré ferroelectrics as a substrate for tuning the band structure. So that's it, and I'm happy to take any questions.
So when you make this ferroelectric in-plane sliding motion occur, do you always return to the same set of atomic alignments on the way back?
That's our guess.
I would bet that you don't know the atomic arrangements.
Right.
But you said you had 10 to the 10th duty cycles in the switching, which means if
Right,
you
so
weren't.
we sometimes see that there is a change in the coercive field, which I think means that even if you apply the same electric field, which I think means that it really doesn't go back to the exact same position. Maybe or as you slide it, sometimes it goes over the pinning of some size and go to the farther away or from the device. That's our guess, but I think it'll be nice if we can directly visualize it while we are applying the electric field.
Have you guys ever tried putting some in-plane strain on there and seeing if you could make a stick slip piezo? Right?
So in-plane strain to the
Between the BN layers.
between the BN area. Yeah, I think that'll be interesting. So we will be probably see like kind of stripes of the up and down polarizations.
We might be able to make a stick slip motor if you could bias the direction of the. If you could bias the direction of the sliding, so it always picks the sublattice.
Right. So it's kind of like we could call it kind of like NEMS, like nanoscale actuator. I'm not sure if it could be useful for something or not, but yeah, I think that'll be very interesting.
So this sort of moiré ferroelectric pattern, can you also use that for like second harmonic generation as a quasi-periodic structure?
By using this substrate.
Yes.
Yes, I think just like what people do in the periodically modulated structures, I think that would be also interesting. I haven't really explored much, but maybe we should. Do you guys work on these kinds of things? Or
You want to?
okay, maybe we should talk about it. Any other questions?
Yeah, for the BN electricity, there seems to have a interface. There is a step of the right line. So I guess
This.
yeah, I guess
Yeah.
there could be like some defect that pins the domain.
Yeah, so that's actually exactly the things that we discussed here.
Yeah, but
So-
however, on the opposite direction you go back,
Mhm.
and the blue line, there is no such intermediate phase.
Right. And again, it's hard to know what's exactly going on with the real space imaging. But yeah, it seems to see the asymmetry between the one switching from down to up, one up to down. Yes. Thank you very much.
There are no questions. We'd thank the speaker once again.
Should we know if the boron and nitrogen will align? I mean,
So sort of C2MR. What they said.
Let's
Funky mask.
I think it looks something like
Five
this.
things for Chris.
That's, I'm
I
pretty
mean,
sure.
other than the calculated polarization magnitude
Right.
matching what you measured experimentally. From that, you can infer
Right,
the atomic structure.
we don't do that, but some other groups does it for the TMDs. I'm not quite sure for the